There is a place on Mars where scientists know the exact coordinates. They know precisely when, each year, it begins to change. And yet they will not send a robot there to take a closer look. The reason for that hesitation, strangely enough, has everything to do with what might actually be there. On the slopes of the red planet, narrow, dark streaks appear every warm season. They grow downhill, darkening week by week, then fade when temperatures drop. The following season, they return to the same slopes, flowing in the same direction, year after year. Nobody can explain why. If this is water, where is it coming from on a planet whose atmosphere is so thin that liquid water would boil, freeze, or evaporate before it could travel any distance at all? And if it is just dry sand, why does sand seem to know exactly which season to slide? Science does not have a definitive answer. But what truly unsettles researchers is not the mystery itself. It is the fact that the place most likely to hold the answer is the place they are least permitted to approach. The more potential a site has for harbouring something extraordinary, the more carefully it must be preserved from the very people trying to understand it. In 2006, NASA placed the Mars Reconnaissance Orbiter into orbit around Mars. The spacecraft carried 6 scientific instruments, but the one that made it truly remarkable was a camera called HiRISE, short for High Resolution Imaging Science Experiment. Shooting from hundreds of kilometers above the surface, HiRISE captured images at a resolution of 25 centimeters per pixel, making it one of the sharpest tools ever sent to observe the surface of another planet. More importantly, it photographed the same locations repeatedly across different seasons, giving scientists the ability to detect subtle changes that a single snapshot would never reveal. In 2010, Luhendra Ojha, then an undergraduate student at the University of Arizona, was working through HiRISE images of the southern highlands of Mars. His task was straightforward: compare seasonal imagery and look for geological changes. Then he saw them, narrow, dark lines on steep slopes, not appearing all at once, but gradually lengthening over weeks during the warm season, then fading as temperatures fell, then returning to nearly the same positions the following year. Ojha brought the discovery to Alfred McEwen, the lead scientist behind HiRISE. McEwen did not dismiss it. He expanded the search across other regions of Mars. What came back was not an isolated anomaly. These features appeared at dozens of sites, across different terrain types at various latitudes around the planet. The research team named them recurring slope lineae, or RSL for short, translated plainly, repeating lines on slopes, a deliberately neutral name that made no assumptions about what they actually were, because from the very beginning, nobody felt confident enough to. There was one possibility that nobody felt comfortable ruling out from the start: water. And on Mars, simply saying that word out loud is enough to change everything. Mars today is a frozen desert. Its surface has not seen a drop of rain in billions of years. Atmospheric pressure there is so low that if you poured a glass of water onto the ground, it would not flow. It would boil and evaporate almost instantly, even in temperatures well below freezing. Those are the conditions that physics imposes on anything that dares to exist in liquid form on this planet. So when scientists looked at HiRISE imagery and saw dark streaks beginning at a high point on a slope, extending downhill under gravity, appearing in the warm season and vanishing in the cold, the human mind reached for the most familiar explanation. On Earth, things that behave this way tend to be water seeping through soil, thin mud flows after rain, or some kind of liquid finding its way downhill. Mars is not Earth, and images taken from orbit cannot reach down and touch the ground to check. What looks like a flow could just as easily be fine sand sliding down a slope, surface dust disturbed by wind, salts shifting colour as temperatures change, or any number of physical processes that nobody has thought of yet. What made scientists unable to simply move on was the seasonality. Sand slides whenever gravity pulls it. RSL are different. They wait. They appear at the right time of year, grow during the warmest weeks, and fade when the cold returns. Something on those slopes is responding to temperature, and in 2015, scientists thought they knew what it was. On the 28th of September 2015, NASA held a press conference with an announcement that had been kept under wraps until the last possible moment. Speculation had been building in the media for days. When the screen came up, the message was clear. The strongest evidence yet that liquid water flows intermittently on Mars today. Luhendra Ojha, the undergraduate student who had first spotted those dark streaks back in 2010, was by this point a researcher at the Georgia Institute of Technology. He led the team that published the findings in Nature Geoscience. The instrument they used was not HiRISE, but CRISM, the Compact Reconnaissance Imaging Spectrometer for Mars, also aboard the Mars Reconnaissance Orbiter. CRISM does not take pictures. It reads reflected light from the surface to identify the chemical fingerprints of minerals. The results showed that at 4 RSL sites, there were signatures consistent with hydrated salts, specifically magnesium perchlorate, magnesium chlorate, and sodium perchlorate. These signatures only appeared when the dark streaks were at their widest, meaning most active. As the RSL narrowed during the cold season, the salt signals faded along with them. Perhaps most significantly, this was the first time perchlorate had ever been detected from orbit. Previously, it had only been found on the ground by the Phoenix lander and the Curiosity rover. The importance of these salts comes down to chemistry. They dramatically lower the freezing point of water. Some perchlorates can keep water in liquid form down to -70 degrees Celsius. On a planet as cold as Mars, that temperature range opens a small window that pure water could never pass through on its own. To be clear about what this finding actually suggested, if water were involved, it would not be a river or a small lake sitting on the surface. The more plausible scenario was an extremely thin layer of briny moisture soaking into the soil or briefly darkening the surface dust before disappearing. And even if water were confirmed, that alone would not be enough to conclude anything about life. A truly habitable environment also requires an energy source, the right chemistry, sufficient stability, and enough time for life to take hold. Mars had not shown evidence of that complete picture. Global media ran the story everywhere. The public immediately jumped to questions about life. Science remained far more cautious, and as it turned out, that caution had good reason behind it. That reason had a name: Colin Dundas. In 2017, a scientist with the United States Geological Survey published a paper in the same journal that had carried Ojha's findings, Nature Geoscience. His team did not dispute that RSL exist. They did not dispute that hydrated salt signatures had been observed at certain sites. What they questioned was whether those facts actually required a liquid water explanation. Dundas and his colleagues analysed 151 RSL features across 10 different locations. Rather than focusing on chemistry, they looked at geometry, specifically the angle of the slopes where each streak came to an end. What they found was striking. Nearly all RSL terminated on slopes of at least 27 degrees, which is precisely the angle at which dry granular material on Mars begins to slide under gravity. If liquid water were responsible, the flow should have continued onto gentler terrain below. RSL did not do that. They stopped exactly where dry sand would stop. Dundas put it plainly, these slopes look more like the faces of sand dunes than channels carved by flowing water. The second problem was the question of supply. If RSL represents seasonal liquid water that recurs year after year, something has to be providing that water consistently. Mars has no rain, no confirmed underground river has been identified near the surface. Seasonal melting of subsurface ice or the slow rise of shallow groundwater are both possibilities, but each one runs into its own set of problems when tested against the actual data. Then in 2019, a study out of Caltech identified a processing error in CRISM's own data pipeline. In rare cases, signal noise could produce false mineral signatures, including perchlorate. This did not erase the 2015 findings entirely, but it shook the foundation they rested on. So are RSL simply dry sand? Not necessarily. The seasonality remains something that the dry granular flow hypothesis has not fully explained. Sand does not wait for warm weather to slide downhill. RSL do. That question is still open. still unanswered. That unanswered question points to something more uncomfortable. There may never be a single explanation for RSL. Throughout years of debate, a trap formed in both media coverage and public perception. The assumption was that RSL had to be one of two things: water or sand. Mars does not care about that kind of clean categorization. The available data does not tell a single coherent story. The shape and behavior of the streaks suggest flow. Chemical signatures at some locations suggest hydrated salts. The angles at which they terminate suggest dry granular material. Each dataset points in a different direction, and none of them is strong enough on its own to close the question. The more realistic possibility is that RSL do not have a single mechanism. Some streaks may be driven primarily by sand and dust sliding downslope. Others may be influenced by salts absorbing trace moisture from the atmosphere, altering the cohesion of surface material and triggering a granular slide. The same site might be governed by dry processes at one point in the year and influenced by atmospheric moisture at another, or behave entirely differently across different Martian years. The distance from 2015 is real. Science no longer claims that water is flowing across Mars in the way that headlines once led millions of people to imagine. The weight of current evidence leans toward dry processes for most RSL, but most is not all. And until there is direct data collected from the ground at an active RSL site, the story still has gaps. Those dark streaks keep appearing every warm season. The surface of present-day Mars is not static. It is changing in ways that humans can watch from orbit but have not yet been able to touch. And that is precisely the problem. The surface is changing, but humans cannot get close enough to understand why. If RSL have remained a mystery after more than a decade of orbital observation, the obvious question is, why not just drive a rover over to take a direct look? Curiosity has been operating on Mars since 2012. Perseverance landed in 2021. Both carry instruments capable of drilling into rock, analysing chemical composition on the spot, and photographing sediment layers in fine detail. A soil sample collected from an active RSL site could answer in a matter of days what years of orbital debate have failed to resolve. The first obstacle is terrain. Many RSL form on slopes steeper than 27 degrees, which is too unstable for current rovers to navigate safely. Beyond that, landing sites are selected based on scientific value and engineering safety, not proximity to RSL. The distance between where a rover stands and where an RSL is actively forming can span dozens of kilometers of cold, dusty, hazardous ground. But terrain is a problem that better engineering could eventually solve. What actually holds rovers back has a name: planetary protection, the policy of shielding Mars from biological contamination brought from Earth. Spacecraft and rovers, no matter how thoroughly sterilized before launch, can still carry trace amounts of microorganisms or organic material. If a location on Mars has any real potential to harbour liquid water or conditions related to life, sending an Earth-built robot, there risks contaminating the very environment being studied. Once that contamination occurs, there is no undoing it, and the answer humanity has been searching for would be permanently clouded by doubt. This is the ethical conflict at the heart of the entire RSL story. The more likely it seems that these streaks involve water or life-related conditions, the more scientifically valuable they become, and the more strictly they must be protected from the very people who want to investigate them. That is not a contradiction born from bureaucracy. It is the logical result of not yet knowing enough to act without causing harm. Picture a rover sitting a few kilometers from a slope covered in active RSL. No wall blocking it. No physical barrier. Just an invisible line drawn by human judgment. Because sometimes the most dangerous question is not whether you are willing to get closer, but whether you should. What is the greater risk? Missing the chance to find life, or accidentally carrying Earth life to the place you're trying to examine? That question is not new. Mars has been putting humans in versions of this situation long before RSL were ever discovered. In the 1970s, 2 Viking landers touched down on the Martian surface and conducted biological experiments directly in the soil, something that has not been repeated since. The results of those experiments have never been interpreted consistently. Some scientists read the data as evidence of unusual chemical activity. Others concluded it was nothing more than inorganic reactions in the soil. 50 years later, the debate has not fully closed. That is a pattern Mars has repeated throughout the history of its exploration. This planet rarely refuses entirely. It always leaves just enough to keep people asking. The way humans have understood Mars has shifted with every generation. From a world that might resemble Earth to a cold and barren wasteland after the first missions arrived, to something more complicated again when orbital surveys uncovered traces of ancient riverbeds, dry lake floors, and minerals that only form in the presence of water. The question never disappeared. It just moved. From could Mars be like Earth to could Mars once have supported life? And now, because of RSL, another layer has been added. Could present-day Mars still contain small, localized, fleeting pockets of conditions where something might survive, even briefly? RSL are the latest chapter in that same old pattern, a signal clear enough that it cannot be ignored, but not certain enough to allow a conclusion. Mars has never given anyone an easy answer. The answer has not come because exploring a planet from a distance carries limitations that no current tool can fully overcome. High-rise images are sharp enough to spot individual boulders, but they cannot reach down and touch the ground to verify what they show. XRISM reads chemical signals from orbit, but chemical signals do not explain the physical mechanism that produced them. More than a decade of seasonal observations has built up, but recurring seasonal behaviour does not automatically prove cause. Rovers are present on the surface, but they are held back by terrain and by rules that humans themselves established. Every instrument has its own blind spot, and none of them fills the blind spot of the others. That is why RSL remain an open question after more than 10 years. Sometimes the hardest part of science is not finding something strange. It is proving what that strange thing actually means. Looking back at 2015, there was no cover-up, no withheld data. A major finding, when it goes through the process of scientific scrutiny, gets challenged, refined, reinterpreted. That is how science protects itself from reaching conclusions before the evidence is ready. But that caution carries a cost. The big questions about Mars stretch on year after year, while those dark streaks keep reappearing every warm season, completely indifferent to whether humans have worked out their explanation yet. That is the boundary RSL forces us to stand at, between what can be seen and what can be confirmed, between hope and proof. From orbit, those two things look very similar, but the distance between them, it turns out, is enormous. Somewhere on Mars, the warm season arrives. Temperatures climb day by day, and on a slope that nobody is standing on, a dark streak begins to form, growing downhill, deepening, then fading again as the cold returns. Nobody witnesses it directly, only HiRISE, hundreds of kilometers above, photographs what remains after the fact. After more than a decade of watching, humans have orbital images, chemical data, and years of seasonal records. What they do not have is a single soil sample taken from the exact place where this phenomenon is actively happening. The gap between what can be seen and what can be confirmed has not been closed. Most of the current evidence points toward dry processes, but the seasonality of RSL still has not been fully explained. And until there is direct ground-level data from an active site, the story still has room in it. There is a place on Mars where scientists know the exact coordinates and know precisely when each year it begins to change, but still will not send a robot to check. That sentence was true the day Oja first noticed those dark streaks on his screen in 2010. It remains true today. The question is no longer water or sand. The question is when humans will finally get close enough to know for certain what is actually moving on those slopes. If this story made you look at the night sky a little differently, subscribe so you do not miss what comes next. Every week we take you into corners of the universe that textbooks have not caught up with yet, and drop a comment below. What do you think is sliding down those slopes? Water, sand, or something humans have not thought of yet?